In this video, we'll look at the first long question from section 2 of the 2017 exam. In the first part of this question, a ball is dropped in artificial gravity of strength 0.4 times the current time, meters per second. And we are supposed to decide which of the following 5 VT graphs correctly describes the motion. So first of all, we should focus on the general shape of the graph. So what do you think the shape should look like? We have constantly increasing acceleration, positive acceleration, so we are really looking for a VT graph which is curving up. This straight line is constant acceleration, and the constant line would be constant speed, and that means no acceleration at all. So we can rule out A and C, we'll eliminate them, they're the completely wrong shape. To decide between the 3 remaining graphs, we will have to look at some points and see which is the best shape, which fits the numeric values. For that, we'll use a formula which you might not know, but you definitely know a similar formula. So here I say that speed equals half the jerk times the time squared, where the jerk is the change in acceleration with time, so it's the next step. Distance, speed, acceleration, jerk. Third derivative of distance with time. And as you can see, it's the same as the formula you're familiar with, one of the Suvat's equations, that S equals half AT squared, and we just move up by one derivative. So distance changes to speed and acceleration changes to jerk. This allows us to find the speed for any given time. And we'll look at 2 times, 0.8 and 1 second. And when we plug into the formula, we see that the correct speed for time equals 1 is 0.2 meters per second, and 0.8 seconds is 0.13 meters per second. And the only one graph which contains these 2 points of the 3 which have the right shape is B. For time 0.8, we have 0.13, and for time 1 second, that's 0.2. And so B is our correct answer. And now for the same ball in artificial gravity, we are supposed to find the time taken to fall a height d. So here's a formula you know. The distance is the initial distance plus the initial speed, which you'd normally call u, but because we'll try and generalize here, I call it v naught t plus 1/2 a naught t squared. And that's for constant acceleration. Now, if we have constantly increasing or decreasing acceleration, that means constant jerk, the next derivative, we need to adjust this formula with a term 1/3 factorial, the jerk, t cubed. Note that when we differentiate this term, we get the same formula for speed in terms of jerk, which we were using in the previous section. And now plugging in all our numbers, so the initial position, acceleration, and speed we set to 0, and we only have the jerk 0.4, and that reduces to d equals 1/15 of t cubed. And from that, we can express t as the cube root of 15d, which is the final answer to the section, and it was option A. Now the ball reaches the ground, and it starts bouncing off the floor. And section C asks us to say which of these 3 graphs could be the graph of the distance from the floor against time for this ball. One thing to note is that the strength of gravity is increasing. We know it's an increasing function, 0.4 times t. That means that with every bounce, the same gravitational potential energy, which the ball keeps throughout, no energy is lost, will result in smaller height every time it bounces off. Gravitational potential energy is mgh, and when g increases over the time, then h will decrease gradually. And the only graph in which we see that is P, so only P is possible, and that's option A. In part D, we are supposed to say which of these 5 is a suitable unit of force. Whenever we have a question like that about units, it's good to think of all the possible formulas we know for that given quantity. So one we know for a force, this is probably the simplest one, is that it's mass times acceleration. And we know the SI units for both mass and acceleration. So the unit Newton is the same as kilogram from the mass times meter per second from acceleration. And that means that option C is the correct one. And that was our final answer. On a similar note, in part E, we are supposed to figure out what the units of x are, of a quantity x, which figures in this formula for drag in terms of the density of the medium, speed, and area. So this is what all the different quantities are: force, density, speed, and area. And If you want, you can now stop the video and try and write down the SI units for each of these 4 quantities. So force, as we know from the previous section, is kilogram meter per second per second. Then we have this x, which has an unknown unit, the unit of x. Kilogram per meter cubed, that's a unit of density. Then meter per second squared for speed squared, and area meters squared. And when we simplify the right-hand side, we'll see that the meters will cancel to leave only 1 meter to the first power. And that's great because the expressions on both sides are the same. So these parts will cancel, kilogram meter per second, that they are newtons, as we know from the previous section, and that leaves x with no units at all. It's dimensionless. It's just a dimensionless constant, which in this Newton's drag formula, in fact, describes the shape of the object in question. And x being dimensionless was option E in the exam.